Okay, so I will be talking about topological entropy of Bunimovich stadium billiards. So it will be not one dimension, but two dimensions, and that's my co-author, Hongkun Zhang. So what are Bunimovich stadium billiards? Stadium is basically what? Two segments parallel and two half circles at the end. And now I draw it as a very long stadium because we will be considering what happens if the width stays fixed but the length goes to infinity. Maybe from the point of view of playing whatever games, football, such a stadium is not very good, but for mathematical purposes, it's very good. Now, what is a billiard? Okay, that's the obvious thing. Probably everybody knows it. So there is a point which moves inside. When it hits the wall, it reflects according to the natural laws. So the angle of incidence is equal to the angle of reflection. Now the billiards, what are the various properties of billiards? What are good properties of dynamical systems? Maybe first, you can look at the billiard in two ways. One way is the flow. So it's inside the billiard table. Another way is that you only look at the moments of collision with the boundary. So then it is not a flow, but it's a discrete dynamical system. So you start at some point, go in some direction. Okay, so this is point, and here is the next point. And of course, you have to take into account both the point and the angle. So the phase space of a billiard is the product of the boundary and the interval between minus pi half and pi half of angles of reflection. So minus 90 degrees to 90 degrees. Of course, the angle is measured from the normal. So that's why it's not 0 to pi, but minus pi half to pi half. And now, what are the best dynamical systems? The best dynamical systems are hyperbolic. And you get hyperbolic dynamical systems very easily when the boundary from which you reflect is convex. Okay, so how to show it? Oh, something like this. Oh, and you go and reflect, and this is because if you go with a parallel trajectories, then they start to spread. And
sorry, Michał, are you writing something? Because
you don't see me?
No.
Yeah.
Sorry. Sorry. Yes, yes. I see you.
You should look at what kind of view you have. So since usually part of the talk is hand waving,
okay,
then it's a good idea that you can see the PDF file and me.
Perfect.
I
I
want to make it as similar as possible to the usual. Okay. So here I have the boundary of the billiard. I have the parallel trajectories, and then they spread. And this spreading is the reason for hyperbolicity. So there was for a long time a question, can you get something like hyperbolicity when the components of the boundary are not are focusing? Okay, so like half circle here when you go from inside. Now I'm showing on the PDF. I hope you can see it. So, and you want hyperbolicity. And then at a certain moment, I don't remember which year it was, Bunimovich produced a stadium and proved that indeed this is the case. So, as I said, the boundary consists of two semicircles, one on the right, one on the left. Of course, you can think about it up and down, but I prefer this way because it's easier to make pictures which don't take too much space this way. And segments of straight lines. So, what was proof? Ergodicity, K-mixing, Bernoulli property for the natural measure. Now, what is natural measure? Natural measure is when you take this product of the boundary with the interval minus pi half, is absolutely continuous with respect to the Lebesgue measure with the density constant time cosine phi. Phi is the angle of reflection. And C is the normalizing constant because you want a probability measure. Now, the fact that there is this natural measure is why people basically looked at the billiards from measure point of view. So from the point of view of ergodic theory. But we want to study topological entropy. So we should look at this as a topological dynamical system. Okay, so, and then, as I said, most authors are looking at it at measure preserving transformation. So whatever they prove it almost everywhere, not everywhere. And from topological point of view, this is not a good thing because you can think about systems, so even maps of an interval where with respect to the Lebesgue measure, nothing interesting happens. But from topological point of view, various interesting things happen, positive topological entropy. Okay, and another problem with looking from topological point of view at those systems is that it's only piecewise continuous, not continuous. So the situation is similar to what Jerome was talking about this morning. So that it's not continuous, it's piecewise continuous. And even sometimes it's not defined everywhere because where do you go? You have this point where the semicircle meets the straight line and the angle is pi over 2. So you go this way and how do you reflect? not clear, absolutely. So what we do, we found a subspace of the phase space, which is compact, invariant, and the billiard is continuous. Then we compute topological entropy of this map restricted to this subspace. And now, for the whole system, you can try to define topological entropy in various ways. One way, for example, would be to make some coding, so some map to the symbolic system, and then look at the topological entropy of the symbolic system. Some people tried, for example, to look at the number of periodic orbits of various periods and look how this increases exponentially as the period goes to infinity, or other ways. But no matter which way you choose, which way of defining topological entropy of the whole system you choose, if you choose it, if you do it in some reasonable way, then if you have a subset of the whole system, then the topological entropy on this subset, which is invariant, assume, is not larger than the topological entropy of the whole system. So if we find this compact invariant subset on which billiard is continuous, then topological entropy on this set is a lower bound of topological entropy of the whole billiard. And finally, we find the limit of our estimates at the length of the billiard table goes to infinity. Okay, and here the situation that we have only piecewise continuous map is similar as for piecewise continuous, piecewise monotone interval maps, or circle maps like we heard this morning. Or yesterday also, there were those Lorentz maps which were piecewise continuous. And so what people usually do then, as I said already, use some coding to produce a symbolic system. And basically we look for number of pieces of continuity and monotonicity for the iterate. And on the symbolic system, we have the usual shift and the topological, and many people define the topological entropy of the piecewise monotone, piecewise continuous map of an interval, just as the topological entropy of the symbolic system. But for interval, it's even better, because if you use the usual Bauen's or Bauen-Dinaburg, some people say, definition of entropy, so the definition where you count the n epsilon separated or n epsilon spanning sets, cardinality of those sets, take 1 over n logarithm, go to infinity with n, then go to 0 with epsilon. Then if for piecewise continuous, piecewise monotone, with finitely many pieces, of course, map of an interval, you use this definition, you get the same result for topological entropy as for symbolic system. By the way, coming back to the possible definitions of the entropy for the billiard. There are many. Sometimes I said 100, probably slightly less, but not much less definitions of topological entropy if the space is non-compact. There were times when it was a good sport to find a new definition, prove that this is the same as some other definitions and different than some other definitions. So there are many of those. But for those definitions, again, if you take a subset which is invariant compact and the function is continuous, this is the lower estimate of the entropy of the full system. Okay, so we have the billiard, and we want to make coding. So for a point whose trajectory is disjoint from S. Now, did I say what M and S is? Of course I didn't. Okay, this is what happens when you copy paste from the place where there are more details. So M is the boundary and S is the singular set. So in this case, those 4 points when the straight line meets a semicircle. Okay, and then you divide your boundary into pieces and make coding. So what is the itinerary of the trajectory? Now I'm talking about the discrete system. So from the boundary to the boundary. Okay, and capital the script F is the map. And of course, it should be not f of x, but fn of x. Okay, so we get a symbolic system, but this symbolic system, the set of itineraries, is not closed in the product topology, of course, as usually for symbolic systems. We use product topology. Okay, so we have to take the closure of this set. And so we add some set. But then the question is, okay, maybe the topological entropy of this big set on this big set is something, but before we added it, it wasn't as that big, that this entropy sits on the set which we add. So we have to be very careful. Okay, now for Sinai billiards, which are the standard hyperbolic billiards, there was a paper of Baladi and Demers, they were considering topological entropy and proved a lot of nice results. But the situation here is slightly more, not necessarily more difficult at all, but some aspects are more difficult. The situation is different. Okay, and by the way, there is one additional problem here with Bunimovich stadium. When you want to make coding, the natural idea is to divide your boundary into 4 pieces. So the one straight segment, the other one half circle, the other half circle. But the problem is that for the general trajectory, when you go from, say, upper straight segment to the lower one, and you want your trajectory to reflect twice from a semicircle. It may happen that it reflects from the semicircle close to the top, then lower, and then goes to the lower straight piece. But it may happen that it reflects low, then goes up and goes to the lower straight piece. And then you can extend those trajectories both forward and backward. But here they have the same itinerary, at least this piece of itinerary, but it's completely different situation. So you can get two itineraries which are completely the same, but these are two different trajectories. So really you have to take 6 pieces. So when you, for your coding, so 6 states or 6 letters of the alphabet, because on a semicircle, you have to not only know that this is this semicircle, but whether you're going down or up. Okay, so we consider this stadium billiard table with a radius of semicircles 1 and the length of straight segments L. Oh, L will go to infinity later. At this moment, we assume that it's larger than 1. So the phase space, now you have the notation, the phase space M sub L, because it depends on L, the map by F sub L. And then we take the subspace, and we want to avoid this situation with double or multiple reflections from the same semicircle. So we have a subspace consisting of points whose trajectories have no 2 consecutive collisions with the same semicircle. And this will be K sub L. So, and then a subspace of this subspace, KLN. So then there are no n+1 consecutive collisions with the straight segments. Okay, and now I said we take large n, so in some moment we will be assuming that L is larger than 2n+2. And then this map will have very good properties. Okay, so as I said, usually it needs 6 symbols. And additional, we have to specify whether we go up and down there. But since we assume that there are no multiple consecutive collisions with the same semicircle, then 4 pieces are enough. And it also implies, our assumption implies that in K sub L, the angle phi is uniformly bounded away from plus or minus pi half. Oh, you can see it easily, because close to plus or minus pi half it means close to tangent. Of course, if it's close to tangent, then the next time of the previous time there will be collision with the same semicircle. So it's bounded away from plus or minus pi half. So, okay, the singular set in the whole phase space is avoided. Okay, so we have 4 symbols. We make coding. And for every element, for every code, there is a unique point with that itinerary. However, the same point of KL may have more than one itinerary because there are 4 points on the boundary that belong to 2 pieces of the boundary each. So there are those points where the straight line meets semicircle. So then you have to choose whether you choose this piece or that piece. And here already we can use our assumption that L is sufficiently large, because then the angle phi of reflection at any point in our small space, whose first coordinate is on the straight line piece, is larger than pi divided by 4, than 45 degrees. Okay, so
sorry, Michał, we have a question.
Yes.
Why only 4 points when you have 6 pieces? This is a question written in the chat.
Now I have 4 pieces.
4, yes.
Yes, I'm assuming that I'm taking the subspace where there are no 2 consecutive collisions from the same semicircle. And then exactly. 4 pieces is enough.
Okay. Thank you.
Okay, so this is notation. So C is the right semicircle without endpoints. And L1, L2, I think this is the picture, yes. So we take the semicircle, we take a point, and let's say the trajectory comes along L1 and goes along L2. And for I equal 1, 2, the angles between Li and the horizontal line are less than pi over 4, and Li intersects C only at A. And we consider the argument of A as in polar coordinates. And then you can see that the absolute value of this argument is less than pi over 4. Because if you go too low or too high, then one of those lines, L1 or L2, would intersect the semicircle in the second point, and we assume that this doesn't happen. So we have the correspondence between the space KLN and this symbolic system sigma Ln, which is a bijection. And then the next lemma is that, again, if L is sufficiently large, then those systems, KLN with a billiard map and sigma Ln with a shift, are topologically conjugate. Oh, that's kind of easy to prove. And then this coding is good, but we can do a little bit better. We can simplify it. Okay, so the first thing is to identify the symbols corresponding to 2 semicircles. And this can be done due to symmetry. So in such a way you get 2-to-1 factor. And I use the prime for those factors. And of course, if you take 2-to-1 factor, topological entropy does not change. So we can do it. And with this simplification, it's the sigma L prime, it's a closed shift invariant subset, and is a subset of the phase space of some subshift of finite type. And the subshift of finite type, which I'm considering, is the following. So there are 3 states, 0, A, and B. So 0 corresponds to semicircles. Now both semicircles are identified. And A and B are lower and upper segments. So there are, all transitions are possible, except you cannot go from the segment to itself. From the segment you oh, I think that's not true. No, that is true. Okay. I thought for a moment that you cannot go from 0 to 0, but you can, because you can go from right semicircle to the left or vice versa. So you only cannot go from the segment to itself. Okay, so, and sigma Ln prime is closed shift invariant subset of sigma L prime, where additionally n step transitions involving only states A and B are forbidden if the number of steps is larger than n. Because remember, when I took this subscript n, capital N, then I assumed that you cannot have more than n consecutive collisions from the straight pieces. Okay, and now we recode it. So again, some recoding. So we replace states A and B by numbers A. So upper one from 1 to n, lower one from -1 to -n. Okay, and then we record this sequence in the natural way. And maybe the best thing is to look at the picture. So we unfold this billiard. And now we look at the trajectory here. Okay, so this is, if we go up, then we have 1, 2, and get to 0 again. So this semicircle is coded at 0. And here we go 1, 2. Or if we go this way, we get -1, -2, -3, and 0 again. Okay. And this recoding, you can easily check, is topological conjugacy. So the system that we get, that we had, is topologically conjugate to a subsystem, which is the following subshift of finite type. They are states from -n to n, capital N, of course, and transitions are from 0 to every state. If I is between 1 and capital N -1, you can go to 0, you can go to I + 1, so you can go to semicircle or to the next level. And if you are below, so if I is, of course, this should be This is minus I. So minus I is between 1 and then minus 1. So from I minus I, you can go lower to minus I minus 1, and you can go to 0. Okay. And then again, for L sufficiently large, this system and this system are topologically conjugate. And this picture was supposed to illustrate something that okay, I already remember. So what is the idea of the proof? The idea of the proof is just variational proof. So you want to show that you can kind of realize every trajectory for your code. And how do you realize? You take all curves, all, not curves, all things that could be trajectories in this picture. So suppose I want to show that I can go from 2 to 0 to minus 1 to 1 and again to 2. So I fix the beginning and the end at 2, and I take all broken lines, which are candidates for trajectories, so which go from 2 to where I wanted to 0. So a straight line here, then straight line here, straight line here, straight line here. I look at all of them and I take the longest one in this space of not quite trajectories, candidates for trajectories. And it turns out that the longest one is actually a trajectory of the flow. So the incidence and the reflection angles are the same, which is basically easy to see, because if you fix the 2 points and the third is somewhere there, so you go from the first point to the second to the third, and you fix the first and the third, then the position of the second point where the sum of the lengths is the same, of course, is an ellipse. And if L is sufficiently large, this ellipse is tangent to the semicircle from the outside. So the longest candidate for the trajectory is a trajectory. Okay. And now I see some chat. Can the longest trajectory hit an endpoint of the semicircle? Yes, that's a very good question. And it cannot hit this end of the semicircle, and even it cannot hit the circle again. Okay, because the problem is not only the end of semicircle, but I take this longest curve, but maybe it intersects our semicircle twice. Okay, but if you look at the geometry of the thing, if it intersects the semicircle twice, which of course is a special case if it hits the end of this endpoint of the semicircle, then the angle, then at least one of those angles is too large, larger than 45 degrees. So, okay, that's the simple geometry of that. Okay, now what is the transition now? Computation of the entropy, computation of topological entropy. Well, it's subshift of finite type, the sigma L prime C, and small sigma is the shift. Okay, and we cannot go from A to A and from B to B. So these are zeros, the rest are ones. So characteristic polynomial is this. So the entropy is the largest zero of the characteristic polynomial, which is logarithm of it. So that's logarithm of 1 plus square root of 2. So the topological entropy of this system is logarithm of 1 plus square root 2. Now, what about this system when we recode it and we have our n? And of course, we assume that L is larger than 2n plus 2 or whatever it was. 2n plus 2, yes. And then the entropy of the system is the logarithm of the largest root of this equation. And how do you compute it? Okay, we know the transition matrix of the system, but it's easier not to look at transition matrix, but transition graph, directed graph. And for this directed graph, we compute the entropy using a Rome method. So we find the Rome, I think it consists of 1, maybe 2, or maybe 2 points. And the Rome is such a subset of vertices of this directed graph that every loop in this graph must pass through at least one of those. So every path leads to a Rome, to Rome. And then there is the formula from the paper Bigamy. If you know this paper, or from the book with Louis and Jaume, how to compute the entropy. And it's this. And then you see that if n goes to infinity, oh, that's kind of easy, then the largest root of this equation converges to the largest root of this equation. This x squared minus 2x minus 1 equals 0. So if L is larger than 2n plus 2, then topological entropy of the system is the logarithm of the largest root of this equation here. And then independently of which definition of the entropy we choose, we have the lower limit of the entropy of FL restricted to KL, which is of course less than or equal to the entropy of the whole system, whichever definition we choose, it's larger than or equal to 1 plus square root of 2. So we have the lower bound which we wanted. And okay, I should, so today is the day when the speakers finish earlier, but maybe I want to say several words about possible generalizations. are working with Hong-Kun on generalization of that. In fact, we some time ago, now we are, at this moment, we are not working, but we'll continue because already we wrote something. And if I can switch to sharing different thing, whiteboard. Oh, I don't have whiteboard, so I have to. Well, what happens? One moment. Share screen. Oh, here. Okay. So do you see my whiteboard?
Yes.
Good. Okay, so if you have, oh, suppose this is a straight line, and suppose they are horizontal. You can kind of turn your monitor a little bit. So, and suppose we have a billiard where here we don't have a semicircle, but we have something strange.
Mm-hmm.
Something like that, okay?
The same, both sides?
No, no.
Okay.
And can we prove something similar? And it turns out we prove, as long as there is on both sides such a point where the tangent line is vertical, and when you look in this direction, you can see the other side. Okay, here I have such 2 points. And those 2 points can be, okay, they are not necessarily of the same convexity. There may be this and this, there may be this and this, there may be this and this. And the curvature at those points should be non-zero. And then you do a similar thing, except that because of those possibilities, you cannot hope that you can use the longest curve in the space of your candidates for trajectories. Because definitely in this case, you cannot use the longest curve. Maybe you could choose the shortest, but in this case, no shortest, no longest. So what you have to prove, that locally, what happens is that when you come to this place with the kind of bundle of trajectories, those bundle of trajectories reflects in such a way that you get again a bundle of trajectories which spread. And then you come to the next place, you take a part of this bundle of trajectories, which you localize it, and again they spread, and so on. Of course, they spread only if the number L is sufficiently large. But still this works. So here the similar results can be obtained. And of course, you can think also about the situation when those two straight lines, or imagine they are straight lines, are not parallel. Maybe something can be done then, but then there is a problem when you want to unfold everything. Then you will not get this long thing, but you will get something which goes in circles. And then how do you produce a trajectory? That may be difficult. We really didn't think about it. Okay, but this is all. Thank you.
Thank you very much, Michał. It has been very, very, very fun.